Hello everybody, how's the audio? Great. Thank you for being here. It's great to see so many people interested in writing clean code. It's a very cool venue as well. I've never given a talk in an actual theater, so that's very nice. My name is Miro Cupak. I work at a company called DNA Stack, which is a Canadian company where we developed a cloud platform for genomics. But I'm here today to talk about Java. At DNA Stack we do a lot of Java development. We're not actually running Java 9 in production yet, we're still on Java 8. But I've been playing around with it for a while, and I'm also really passionate about clean code, so I thought I would combine the two and basically prepare a talk about what's new in Java 9 and Java 10, and how that affects our ability to write cleaner code. So we're particularly focusing on smaller things, convenience methods and various APIs that allow us to clean things up, as opposed to really big features that people typically talk about. Now, you may have noticed that this talk was advertised as a Java 9 talk, but here in the title it actually says Java 9 Plus. The reason for that is basically Java 10 came out after we scheduled the talk, and I thought, why should we talk about something that's essentially obsolete? Let's talk about the latest and greatest, right? So we'll cover both Java 9 and Java 10. Obviously, Java 9 is the big release here. Java 9 came out about 3.5 years after Java 8, which is a long time in software. So you can imagine that many features had the time to make it into the release during those 3.5 years. In comparison, Java 10 is relatively small, came out in March, 6 months after Java 9. And actually contains mostly low-level features and optimizations. There are, however, a few interesting things that we'll touch on. So, I think I should start by clarifying what clean code is. And I'm sure everybody kind of intuitively knows what it means. If you've attended the keynote today, it actually provided a very nice introduction and background information for my talk as well, coincidentally. So that's great. Most of you have probably seen these two comic strips. I also like the definition from William Zinsser, who actually has nothing to do with coding, but he wrote a lot about writing in English, particularly English as a second language, and he identified 4 principles of writing good English. And those principles are clarity, simplicity, brevity, and humanity. And I think this is pretty applicable to code as well. You want your code to be clear, you want it to be simple, you want it to be short, and you want it to be human readable. So there's a really big focus on the reader, because it's a well-known fact that we actually spend a lot more time reading code than we spend writing it. On top of that, if we focus on reading code, we actually have stricter requirements than when it comes to writing. Because when you're writing the code, you have all the context in your head. When you're reading the code, you're often switching quickly, and it just needs to be, even clearer and even easier to understand. There are 2 very good books on writing readable code in Java. There's Clean Code and there's Effective Java. They're very well known, so odds are you've read them before. If you haven't, I can highly recommend doing so. They're probably the best software engineering books that I have ever read, and they actually provided a lot of information for this talk as well. So the kind of features we're talking about today are factory methods for collections, improved try with resources statement, private methods in interfaces, stream API enhancements, extensions to optional, HTTP to client, and finally, type inference. So we're going to demonstrate all these examples in JShell, which itself is a new feature in Java 9. So before we get to that, let me actually show you JShell a bit. So JShell is what you're seeing here. I hope the font is big enough. Yeah? Great. JShell is Java's implementation of REPL, read eval print loop. So it's a tool that loops continuously reads your input, evaluates it, and prints out the output. So it's very similar to tools that you probably know from other programming languages, Groovy, Scala, Python. They have all had that for a while. And finally, with Java 9, Java is getting an official REPL too. REPL was primarily designed for learners of the language, but it can be actually a pretty powerful tool for experienced developers as well. It's really useful when you're prototyping, sort of increasingly building more and more complex code, when you're just exploring new APIs, which is primarily what we're going to use it for today, or also when you're switching technology stacks. You worked on a project in Python, you're coming back to Java, you need a reminder of how certain things work. JShell is a perfect tool for that. I also used it during interviews. It's just a nice, well-rounded tool for basically whenever you need to get something done very quickly. Now, JShell is very easy to figure out. The main thing that you need to know is essentially that it accepts 2 types of inputs. There's snippets, so the actual Java code that you want to evaluate, and there's commands to the actual JShell tool, which always start with a slash. And we'll see a few of those throughout this talk. But let's start with something really simple. I'm just going to type 1 plus 1, and you can see that 2 interesting things happen here. First of all, 1 plus 1 equals 2. And second of all, 2 was assigned to something called $1 here. And $1 is an implicit variable that JShell created for me. And it does that whenever you have an expression that you don't assign to anything. I could have, of course, created my own named variable. I can just do something like this, and I would have a named variable x. JShell provides a couple of keyboard shortcuts. You've seen me use the first one here. Shift, Tab, and V introduces a new variable, and it infers the type of that variable from the expression. There's also sort of standard tab completion, as you would expect from any other shell. If I wanted to print out this variable, for example, I can just take advantage of the tab completion here, and just do something like this, and I would print out my variable. There are also a few syntactic shortcuts, if you will. For example, you've noticed that to evaluate the expression, I didn't need to wrap it in anything. Similarly, I didn't need to use a semicolon at the end of my statement. And I also wouldn't need to worry about catching exceptions, even checked exceptions. For example, if I wanted to put JShell to sleep for a bit, I can just do thread sleep, which, by the way, throws interrupted exception. That's a checked exception. But I don't need to worry about that for now. I can just do something like this, and it's going to work just fine. So a couple of sort of simplifications to make it easier for us to prototype very quickly. So this brings us to the first commands. The first command is actually vars, which lists all the variables that I've declared. And you can see that I have a few of those here. There's some stuff that I prepared from before as well. We also have methods, and we have types. And similarly, we also have the command list, which just lists all the active snippets. By the way, JShell has this prefix matching going on, so as long as you specify a unique prefix of a command, it's going to find and execute it correctly. So I could have just done something like this. And finally, last but not least, there's a command called help, which essentially tells you everything that you need to know about JShell and everything that you can do within JShell. It's actually pretty well documented, so you can find all the information there. And that's pretty much all that you need to know about JShell, really. So let's move on to the first API. And that's factory methods for collections. Basically, Java9 makes it really easy to create immutable collections, which is something that was relatively tedious to do with the previous releases of the platform. And I'm sure everybody knows the drill. If I wanted to create, let's say, a set, I can just do something like this, say a set of string, and let's call this a set, and make it an interface. Then, to actually add elements to it, I would call the method add. Let's do something like this. Let's just do a few. And finally, to make it immutable, I would wrap it in collections unmodifiable set. Now, there are a couple of problems with this approach. First of all, it's pretty verbose. I needed, like 5 lines of code to create a very simple set. That's not ideal. And the fact that it's not a one-liner is actually pretty annoying, because if you have static collections, for example, you need to use static initializer blocks, which is not very cool. It's also not really an immutable collection. It's more like an immutable view of the underlying collection. But if I kept the reference to the original set, which I have in fact here, I would still be able to modify it. And there's performance overhead associated with supporting mutability in the underlying collection. So in fact, we could also be doing better from a performance perspective. And that's exactly what Java9 does. So Java9 introduces truly immutable collections that you can obtain through static factory methods on all the main interfaces, list, set, and map. So for example, if I wanted to create an immutable list, I can just use the method of here, and if we take a look here, you can see that there's quite a few versions of it. It's overloaded 12 times to be exact. So it's always 0 to 10 arguments, and then there's a single var method. So you might be thinking, why do we have it structured like this, right? Surely the var case captures all the other use cases, so why are we polluting the API here? And the reason is performance. There's basically performance overhead associated with allocating the array to back the var arc. So if you're creating reasonably small collections, which presumably is the vast majority of use cases, then you want to avoid this penalty. So if I wanted to create an immutable list, I can just do something like this, and let's call it a list. And then if I try to add something to this list, Java is going to complain, because indeed, this is immutable. In fact, if I take a look at the class here, it's going to tell me that it's not my standard array list. It's a very special implementation of a list. And an important thing to note here is that these immutable implementations are not actually a part of the public API, so we can only rely on the interfaces here. On top of that, you can only obtain instances through those static factory methods on the interfaces, which means that they're not inherited. You cannot invoke them from an implementing class, which means that this is pretty much the only way to obtain such a list. And I just wanted to point this out as a really nice design pattern that actually allows the implementation to change in the future. So that's pretty cool. The API for a set is exactly the same. Again, 12 methods, 0 to 10 arguments, and then a single vararg. For a map, it's actually a bit different. And you can't see it here really well because it's such a small window, but it's also 0 to 10 elements, or in this case, 20 because you specify keys and values one after another. But there's no vararg method here. And the reason for that is you can have keys and values that are of different types, but you cannot have two varargs in the same method, right? So what they did here instead, they provided a method called ofEntries, which actually takes a single vararg of type map entry, and there's a convenience method for creating these entries. So I can just do, let's say, something like this, and I would have a map where key is an integer and value is a string. So that's Java9. Java 10 actually takes this a bit further, and Java 10 provides more factory methods that are actually called copy-of. And those factory methods allow us to create immutable copies of other collections. So if I wanted to create a new list, I can just do list copy of my original list. Let's call this list copy, and I would have a new immutable list. And you can give it any collection, so I can also use this to convert between collections. If I wanted to create a set, for example, I can just modify it like this, and I would have a set that contains the elements of the list, preserving the iteration order. So just a nice little addition in Java 10. The API for a map is very similar, with the exception that you cannot actually give it any collection. It only accepts the map, because of course you need to deal with key-value pairs somehow, and that's just the easy way. That's pretty much all there is to it. It's just a nice little convenience API for creating immutable collections. So to recap, you can now obtain immutable collections through of and ofEntries methods. You can create copies using copy-of. It's also kind of a good practice to static import Java-util map entry. That's the convenience method for creating entries. It's really descriptive. You're not giving up any readability. It's completely clean to just static import it. This new approach is less verbose. In fact, it's a one-liner, which means you don't need static initializer blocks, which makes your code a tiny bit cleaner. There's also no need to use any Java 8 workarounds for creating collections as a one-liner. A common way was to pass it through arrays as list or stream. There's just no need for that anymore. Also, no need to use external libraries such as Guava. That's one of the libraries that I used very commonly for creating immutable stuff. You just have it as part of the JDK now. And they're truly immutable, so no need to worry about leaving references behind. They're automatically thread safe, can be shared freely. They have good performance, don't need to bother about immutability, etc. A really good rule of thumb is to actually default to creating immutable collections, which is what people weren't doing too often in Java, just because it's so much easier to create mutable collections. Well, now you don't have that excuse anymore. It's really easy to create immutable stuff, so just do it. So the next thing that I wanted to talk about is improved try-word resources. And try-word resources is a Java 7 feature. Basically, as long as we have some resource that implements auto-closable, I can specify it directly in the try statement, and it's going to be closed automatically. And pretty much everything in the JDK now that represents some sort of a resource that can be closed implements this interface now. So you sort of get this for free. I have an example here, I believe. It's a method called readFile, which actually uses try-word resources. The method basically opens a file, reads it line by line, and prints it to standard output. It's nothing too sophisticated, basically a copy of a file from disk to standard output. So what we're doing here is I'm creating a file input stream, wrapping it in an input stream reader, wrapping it in a buffered reader, standard Java boilerplate. Then I'm actually declaring a new buffered reader so that I can have it managed by try. That's a really common idiom in Java. You need to give a try a new variable so that it can manage it for you. And what you typically have is some sort of a reader or input stream from before, so you just create a new variable, reassign it, and then use that variable to read the whole thing. So obviously, the not so clean part here is the need to declare this extra variable just so that you can have it managed. And that's exactly what Java 9 fixes. So in Java 9, as long as you have a variable that's final, or effectively final, which means that you may not have explicitly declared it's final, but you just never modify it after initializing it, you can use it directly in your try. You don't have to declare a new variable. So in Java 9, I can actually modify this, and I can completely remove the second reader here. Let me just do that real quickly. And I will just use my original reader here. And this should just work just fine. So I can probably demonstrate this if I have a file here. I should have one in TMP, and I don't have it there. So you'll just have to trust me. Okay, so that's private resources. In fact, in Java9, I can do even better. I can, you know what, I'm gonna need that file, so let me just create this here. And let's actually demonstrate this properly. So I created a file, tmp voxxed, which just contains, and it doesn't work. Oh yeah, thank you. Yeah, there's a single line, it just says hello voxxed. But what I wanted to demonstrate is actually a new convenience method that was added in Java9, and that's a method in the input stream API. And input stream actually has a method called transfer to, which allows you to connect it to an output stream. So in such a simple scenario, when I'm actually just reading something and writing it somewhere else, and I'm not doing any transformations, I could easily just take advantage of that method. So I can open a file, input stream to my file, /tmp /voxxed, and then just call transfer to and connect it to my system out, and you can see that this just works the same. So another nice little addition that was made in Java9. I think Java10 actually added this for buffer reader as well. So to recap, you should always use try with resources. There's really no place to use the alt try finally construct where you close your resources in finally. Definitely do not use finalizers. That's completely wrong. Be aware that sometimes you might be able to avoid this. There might be convenience methods in other APIs that already deal with whatever you need to do. In this example, we've seen input stream transfer to. And don't create unnecessary helper objects. You don't need to do that anymore in this try block. So this brings us to private methods in interfaces, and this is actually a really simple feature. As I'm sure everybody knows, since Java 8, the statement that interfaces don't contain implementation is no longer true, right? Java 8 introduced default methods. And the idea was to allow us to evolve the API. You implement the default method in the interface, and then whoever is implementing your interface, if they're aware of the default method, they can override it, of course. If they're not aware of it, they just get the default implementation for free. And I have an example demonstrating this here. Let me just open the interface. It's a very simple interface. It has a single abstract method, not implemented obviously, and then has a default method which just prints that the method was called. I also have a class here which is implementing that interface. So it provides the implementation for the abstract method, again just says the method was called, and is not aware of the default method in any way. And now, if I instantiate this class, I can actually call the abstract method. Of course, I did provide the override. I can also call the default method, even though I didn't do anything about it. And it's just how default methods work. So one problem with this approach is that you couldn't really evolve default methods. Basically, if you got into a situation where you had multiple default methods and they were sharing something, there was no way to extract this to a separate method because that method would become a part of your API and then you would be committed to maintaining it. Similarly, if your method just grew longer, there's no way to sort of structure it better as you would with regular methods. And that's exactly what Java9 fixes. So Java9 adds private methods to interfaces for the use case of basically better separating default method. So in Java9, I can modify my interface here, and I can just add a new private method. Let's just do private void private method. And for consistency, I'm just going to print that this method was called. Private method called. And let's close this, and let's also close this, call this private method from my default method. So we're emulating the scenario where my default method got too big. So I'll just call the private method here. So we modify the interface. Let's try this again. My class, I'm calling the abstract method. Everything works as before, nothing changed. Calling the default method, of course, private method was called as well. And if I try to call the private method directly, this will not work because, of course, it's not a part of my API. So private methods allow us to clean up our interfaces a bit, assuming we're using default methods. So to recap, all the methods should be short. That works for default methods as well, so take advantage of the private methods here. Don't repeat yourself. So if you have multiple default methods sharing stuff, extract it to a new private method. Be aware of the fact that default methods are a perfect tool for providing default behavior when you're creating a new interface, when you're introducing new API. They're not so perfect to actually introduce new functionality to existing APIs that are already in circulation and people might have implemented that. Of course, it was designed with backward compatibility in mind, but you can never maintain all the possible invariants that people could impose on whatever interface they're implementing. So just be very careful about extending existing interfaces. It's probably not a good idea most of the time. So this brings us to the Stream API. And Stream API was actually enhanced in Java9 and 10 in sort of two ways. First of all, the Stream API itself has evolved. And second of all, Stream API was brought into many other parts of the JDK, and many other APIs were made stream-friendly. So I want to demonstrate all these two aspects. One important thing to realize about streams is that they're not suitable for everything, right? Even though you can retrofit them to fit pretty much any problem, that doesn't mean you should. Sometimes you might still be better off just using a for cycle, because a stream would be so complicated it would actually lead to code that's less clean. So it's important to know what you should be using streams for and what you should not be using streams for. And Java9 and 10 essentially make streams suitable for more use cases. And a good example of this is the method iterate, for example. So we take a look here. Let's take an int stream and the method iterate. And I made a typo here. We can see that there are two versions of this. So the first one was available in Java 8. The second one was added in Java 9. And the difference between them is this predicate here. So let's take an example to demonstrate the difference. Let's say I want to print all the even numbers that are less than 100, right? Even numbers less than 100. So a very naive and straightforward way of doing this in Java 8 would be using iterate. Just iterate from 0, increment by 2 in every step. Then I will filter the numbers that are less than 100, and then I will just print everything. Just do print line. And this seems very straightforward, but if I actually try to run it, you can see that it doesn't really work. And the reason this doesn't work is because I actually created an infinite stream, and I did correctly filter the first 100 elements, but the stream kept going, and at some point my integer went over, and suddenly all my integers were less than 100. And there actually wasn't a really good way of dealing with this in Java 8. Or actually, to be precise, in this particular case, I could deal with this easily, because I know that there are exactly 50 even numbers less than 100, right? So I can completely remove this filter here, and I can just replace it with a limit 50, and this will work just fine. But in general, you don't have this benefit. In general, you don't know how many things you're going to get. You only know that you want to keep taking things while a certain condition is met. So that's the kind of functionality that was added in Java 9. So in Java 9, we actually have two new methods, takeWhile and dropWhile, which is basically like versions of limit and skip that take a predicate instead of an absolute value. So I can just replace this filter here with takeWhile, and this is going to work just fine. But I can do even better. In Java 9, I actually don't even need this takeWhile. I can completely remove this stage of the pipeline, and I can just put this condition directly inside my iterate. Remember the second version of iterate. So I can just say, give me numbers less than 100. And again, same result. And if you look at it, it basically reads like a for cycle. And that's essentially what it is. It's like a streamified version of for. So that's iterate, takeWhile, and dropWhile, new Stream API methods in Java9. There's another method I would like to mention, and that's the method called offNullable. So I'm sure you're aware that you can create streams of arbitrary elements in Java9, right? I can just use the method off, and I can create a stream containing something. What I couldn't do is put a null there, because you don't want to have nulls in streams, or collections for that matter. What I can do in Java9, however, is to actually use offNullable, and this is going to go through just fine. But if I take a look at this stream, you can see that it's not a stream containing a null, but it's actually an empty stream. So it's kind of like a convenience method that deals with nulls. So how is this useful? Well, it basically allows you to construct streams in a cleaner way. It's very common when you're using large streams that you have several maps, and at some point you basically end up with nulls in your streams, and you need to filter them out. You don't want to have null pointer exceptions or nulls. Which means that at some point in your pipeline, you will have to have an if statement that does the null check, or some sort of a ternary operator. None of these are very clean, and essentially offNullable allows you to get rid of the null check. It's particularly usable when you combine it with a flood map. So finally, the last thing in the Stream API I wanted to talk about are actually collectors. Java9 adds a couple, and they're interesting, but I don't want to get into too much detail. But Java10 adds several very widely usable collectors, and they basically make the Stream API play nice with immutable collections. So I'm sure that everybody is aware of the standard collectors. The basic ones are toList, toSet, and toMap, right? So I can, for example, collect this to a list, and of course, in this case, it's empty, so I'm not really getting a lot of information here, but that's how this works. In Java10, however, we have unmodifiable list, unmodifiable set, and unmodifiable map. So we can actually create immutable collections from this. So again, just, immutability everywhere. So to the last point about streams being propagated to more APIs, there are a couple of really good examples in JDK 9 and 10 actually, but I just want to show one. And the one example is pattern matching. Pattern matching is, by the way, a great example of something that you can use JShell for. It's something that you don't get right the first time, so it's just really nice to open a JShell and quickly try out some regular expressions. But I'm going to create something really simple here. I will just create a pattern that matches for something super simple, let's say a number, or a single digit rather, and let's call this P, and then I will match on this pattern. Let's give it some string, whatever, I'm just looking for numbers here, and let's call this M. And then I can use the results stream-friendly method here, which actually gives me a stream, and then I can use, for example, a map to extract some information. For example, for each result, give me the group, so in other words, where in the input sequence it matched, and let's print this out. And that's how the pattern matching API plays nice with streams. So, to recap, be aware of the new stream methods, take while, drop while, iterate. Remember that you can create unmodifiable collections now. There are some convenience methods in other APIs, so you might not need to construct streams manually. And avoid unnecessary null checks by using offNullable. So remember that streams are suitable for more use cases now, but not all use cases, so don't overuse them. They can make your code hard to read as well. So we're getting to extensions to optional now, and there are a couple of extensions in the optional API that are actually worth mentioning. So let's take a look at this. Optional is again a feature that was introduced in Java 8. It's basically a container that may or may not contain a non-null value. So it was introduced to reduce the number of places where a null pointer exception can be thrown. The basic API is actually pretty simple. I can create an empty optional, or I can create an optional containing something. And that's basically it. What we also had available was a method called isPresent, which is a Boolean method that checks if there's a value in this optional. And similarly, we also have a method called ifPresent, which checks if there's a value, and if there is a value, it can perform an action on the value. So that's all Java 8 stuff. So now we have a couple of new things in Java 9 and 10, and we actually have 4 methods that all have something to do with handling default values. So the first addition is actually a method ifPresent or else, which I'm sure you can guess how it behaves. It behaves exactly as ifPresent if there is a value, Otherwise, it allows us to specify a runnable to perform. So I can do something like this. Let's say if the optional is empty, just print out that it's empty. And of course, in this case, there was something there, but if I actually replace this with an empty optional, it's going to work nicely. There are two interesting methods in Java 8 that handle default values as well, and I just want to mention them because they tie into what was added in Java 9. And these two methods are or-else and or-else-get. So or-else basically takes a look at the value in the optional. If there is a value, returns it. Otherwise, we can provide a default value. So let me demonstrate this here. You can just use or-else, return empty. Or-else-get is just a more flexible version of this, where we can give it a supplier. So we can do something like this. And Java 9 added a new method, which is the method or. So if you notice, these two methods all deal with the values inside the optional. The method or actually deals with the optional itself. So if I just specify or here, we can actually give it some optional, say an optional containing empty. And this is going to work nicely. So we have values, Java 8. We have optionals, Java 9. So what was added in Java 10? Well, they added exceptions. So in Java 10, there's another method in the family, which is called or-else throw, and that actually throws an exception. There's two versions of it. There's a default one, and there's one where you can give it a supplier for exceptions. I'll just try the default one, and it actually throws a no such element exception. So just some nice additions that allow us to clean up handling of default values. The final method that I wanted to mention here is the method stream. A stream essentially converts an optional to a stream. So if there is a value, you'll end up with a stream that has a single element. If there's no value, you'll end up with an empty stream. And we can demonstrate this here. I'll just convert this to a stream and try to print the values, but of course in this case it's empty. So again, this is just a nice cleanup method. It's basically really useful when you're dealing with streams of optionals. You can kind of convert between them without doing any manual conversions. So to recap, use if present or else instead of the construct where you would have an if statement and then check for is present. We have a method or that provides a clean, fluent way of chaining behaviors and optionals. And just be aware that there's a whole family of or-else methods. We can use streams to take advantage of the lazy nature of streams and handle optionals better. And remember that is present is usually not the best choice for you. All the other methods above are typically a better alternative. So I'm getting a sign we have 3 minutes left, but we actually started really late. So can I go over? Yeah? OK, perfect. So there's two last things that I wanted to show. There's HTTP2 client and type inference. And let's just do this very quickly since we're pressed for time. So Java 9 essentially added a new client API for doing HTTP. So it's much cleaner than the old HTTP URL connection, but it also supports all the cool new things. It supports HTTP2 with TLS, supports WebSockets, server push, proxies, cookies, asynchronous requests, basically everything that you would expect from a modern HTTP client. This API is provided as an incubator module in Java 9. Which means that it's not completely finalized. It lives in a special namespace, and it's not resolved by default. So, but I actually pre-imported it into JShell so that we can use this. I didn't manage to connect to the internet here, but to demonstrate the client, we're obviously going to need a server. And I have a backup here. I will just open a simple HTTP server here, which basically just uses really old functionality from the JDK to construct the simplest possible server that you can have. So it's a server that has a single endpoint, and no matter what you send to that endpoint, it's going to respond with a fixed string. And you can see the setup here. So I'm actually creating a server. I'm giving it port 8000. Then I'm creating the endpoint /hello, attaching my favorite handler to it. And the handler is defined by doing a lambda on an HTTP exchange, which calls handle text. In handle text, I set the status code to 200, everything is OK, and I print out a fixed string that in this case is just hello Voxxed. And then finally, I will start the server. So I'm not going to demonstrate the old HTTP URL connection API. Just trust me, it's really ugly, has side effects. It's not pleasant to use. It's probably the first thing that you pull a library in for. I honestly don't know anybody who uses the HTTP URL connection API. Just use Apache Commons or upgrade to Java9. The new API, however, is very nice and clean. And it's built around three main classes, which are HTTP client, HTTP request, and HTTP response. So let me just demonstrate this. I will just create a simple client here, new HTTP client. Let's call this client. And then I can actually take a look at the client version. We're saying HTTP2. To be fair, I'm not really taking advantage of this. I'm only talking to my local server, but that's fine. We're just focusing on the API here. So then I can build a request, and that actually uses a builder pattern. So I can just give it a URI, let's say new URI HTTP localhost 8000/hello. I call the get method nicely as a method here. And I call build, let's call this request. And then I can use the client to send the request to my server. And this also takes something called a body handler here, but in this case I will just tell it to treat everything as string. Thankfully there's a built-in handler for this, so I'll just use body handler as string, and let's call this response. And hopefully everything works. If we take a look at the status code here, nice fluent API, this is fine. Similarly, body, hello Voxxed. So everything works nicely. So to recap, there's a much cleaner alternative to the old HTTP URL connection. It's built around three classes: HTTP client, HTTP request, HTTP response. You should avoid APIs with side effects, which HTTP URL connection is an example of this. The new client is versatile, flexible, and clean. If I wanted to make this asynchronous, I literally need to change one method call in my previous snippet. And there's benefits for using functionality that's available as part of the JDK, as opposed to external libraries. It's very well tested, it's interoperable, etc. But be aware that it's an incubator module, so maybe not using it in production yet. So, we have a couple of minutes, so let's just blast through the last part, and that's type inference. I really think this is very exciting, so I want to cover this. When we're saying type inference, we're of course referring to the compiler's ability to infer types in places where types are not specified. So that's basically based on the context. So if you're used to other programming languages, such as Scala or C#, what's introduced in Java is probably not new to you. It's just something that has been around there for a while. But Java has some interesting stuff to offer as well. So type inference has been around since Java 1.5, right? We introduced generics, generic methods. That's where it became visible. Then in Java 1.7, we added the diamond operator. Java 1.8 added lambdas, which was very exciting. This was kind of the first situation when we didn't have to specify type when we were introducing a variable, right? For lambdas, you typically don't specify types. So what added Java 9 and 10? Well, Java 9 extended the use of the diamond operator, and Java 10 actually added local variable type inference. So let's take a look at both these things. I just have a quick example here for the diamond operator. Basically, the problem with this was it's almost an inconsistency. You could use it practically everywhere except for anonymous classes. So in this case, I'm actually implementing a supplier interface. It's just a simple hello world supplier. But as you can see, I need to specify the string on both sides here because it's an anonymous class. In Java 9, however, I can actually modify this and just completely remove this string on the right, and it's going to work just fine. So if I call the get method there, you can see that it works nicely. So that's pretty much it, just the ability to use it everywhere, including anonymous classes. So this brings us to Java 10 and its local variable type inference. This type inference is actually very limited compared to other languages. It basically takes a look at your initializer, and that's how it infers the type of the variable. So it really just looks on the right side, and that's what it determines on the left side, basically. Very simple stuff. It's actually limited by design. It's not, that we couldn't do it better. We just didn't want it to be abused. So that's why it's done this way. So how does this look in practice? Well, in practice, you can declare variables using the var keyword. So actually, that's not accurate. I shouldn't be calling it a keyword. It's very important that it's not a keyword, in fact. It's something called a reserved type name. And the fact that it's not a keyword means that if you already have some stuff in your code that's actually called var, such as a variable or a method, it's still going to keep working. It will be confusing, sure, but it will keep working. So we can take advantage of this keyword here, and I will just create a list, let's say new array list of type string. And you can see that this works nicely. And we take a look at the variables here. It actually internally is stored as an array list of type string. So the important thing to mention here, we're not losing static types in Java, right? Java is still statically typed. We're just inferring the types in the background. So you can probably imagine that there's quite a few funny things going on, right? Like this was inferred as an array list, typically would assign to a list. You probably kind of get the feeling that you can do some pretty magical stuff with this when it comes to polymorphism or inheritance. And that's exactly true. That's why there is a very specific set of rules for when you can use this. And let's just show a couple of situations, and let's just do this as a quiz, just mentally try to guess what would happen in this scenario, and just see if you're right. So all the snippets that I will show you would be actually completely valid and will work completely well if you were using explicit types. What we're going to do is replace them with vars and just see if that still works. So let's start with compound declarations. I will just do something like this, which of course would work with ints, but as it turns out, doesn't work with var. Var is not allowed for the compound. Similarly, we can use it in methods. If I, for example, let's create a method, let's say increment, which takes an integer and then increments this integer. This would obviously work. If we use a var as an argument, no, var not allowed. Similarly, if we used it as the return type, it won't work as well. So what about declarations without explicit initialization? What if I do something like this? And it turns out it doesn't work again. Like I said, the type inference is very limited. It just looks on the right side. There's nothing on the right side, so there's nothing to infer. So what if I initialize it to null? No, still not good enough. Null is not very specific. What if I tell it that this is a very specific type of null? Yeah, this works just fine. So how about arrays? Obviously, I can create arrays just like this. Let's just do a really simple one. This works nicely with int. But if I use var as the element type, no, turns out not allowed. It's an element type. What if I use it as the whole array? No, still not allowed. So what if I initialize this array differently? Let's just do something like this. Yeah, turns out this goes through just fine. We can also try lambdas, actually. I will just do a simple supplier here. This obviously would work as a supplier, but it turns out that you actually cannot use vars with lambdas, or method references for that matter. Finally, let's try something like this. Let's combine it with the diamond operator. I will just construct an array list. And you might be surprised to find out that this actually works. But if we take a look at the variable, this gets inferred as array list of type object, which is almost never what you need, right? So just be very careful about this. By the way, if I actually pre-initialized this array with something, let's say integers, this would work fine, and we would actually end up with an array list of integer. And you can do all sorts of funny things with this, particularly if you use it with stuff like anonymous classes. But to wrap up, diamond operator, just use it as you normally would. Use it everywhere, including anonymous classes. Most of the time, you're probably better off using lambdas, but there are still very valid scenarios for using anonymous classes, particularly when you're dealing with abstract classes or interfaces that are not functional, right, that have multiple methods. Local variable type inference does not replace static typing, but it's generally a good thing. You might have the feeling that it actually makes your code less readable, but it's just a matter of getting used to. So I had a similar feeling with lambdas, right? For a very long time, actually, I was specifying explicit type for lambdas. But then after a while, you just get used to it, and you realize that the explicit types actually make it less readable. So I feel like this is going to be the same with local variable type inference. It reduces boilerplate and improves readability. It can actually help with maintenance and refactoring. Imagine if you're replacing some domain class. If you're using explicit types, you need to refactor all the code that uses it. If you're inferring the types automatically, it's going to be done automatically. You don't need to change all that code. Definitely use it for local variables with initializers. That's what it's for. Use it for loops as well. Works both for standard traditional for loops as well as for each. We can't use it for a bunch of scenarios, and we've gone through them, particularly fields and API methods. And basically just think carefully about when to use it. When the generated type is not too obvious, it might kind of affect readability. But in some cases, maybe you have some complex types because you're splitting some complicated streams pipeline. It might actually make it easier for you. So just think about it carefully. Be careful when it comes to primitive types. Type inference works there, but things like byte, short, and long get all inferred as int, so it might not be what you expect. Similarly, be very careful about combining it with the diamond operator and generic methods. Probably not the best idea to use them with anonymous classes either. And it's more important than ever to use very expressive names for variables now. In the absence of types, you might be tempted to use Hungarian notation, which is the thing where you encode the type name in the name of the variable. Don't do it. Let the compiler take care of it. It's still very discouraged in Java. Just name your variables expressively. Don't rely on IDEs. IDEs have features that show you the inferred types, but people read code on GitHub, so don't trust this too much. And try to minimize the scope of local variables. A good rule is basically when you declare the variable and you don't know how to initialize it, odds are you're declaring it too quickly, too early. And if you don't have an initializer, it doesn't work with var. So in fact, the fact that you cannot use var might suggest that you're not minimizing the scope correctly. Use it in for loops. In fact, prefer for to while. You have smaller scope. And keep your method small and focused. Also note that the program to the interface pattern doesn't work here. Type inference always infers the concrete type. But in this case, it's probably a trade-off that we're willing to make because local variables have such a small scope. And that's it. That's everything that I wanted to talk about. So it was kind of a quick, and yeah, I hope you liked it. And if you have any questions, feel free to come down. I'll be around.
Thank you, Miro, for that. So questions. We're taking 3 questions. Anyone? It was all clear? No questions. Wow. You rocked. So if there are no questions, a big round of applause for Miro once more. Thank you.